Have you ever wondered how many sorting algorithms we learned or how many sorting algorithms exist? Well, there are a huge number of sorting algorithms that exist around us. But we have to use the algorithms based on their efficiency. All the algorithms we have used so far have worked with both fractions and integers. But which algorithm can be efficient if we want to sort values within a certain range? Well, bucket sort is mainly useful when input is uniformly distributed over a range. For bucket sort, the set of floating point numbers are in the range from 0 to 1. As we know that there can be infinite numbers between the range 0 to 1, bucket sort is one of the most efficient sorting algorithms to sort the given numbers in this range.
In this video, we will first describe the topic. Then we will discuss the algorithm, how the sorting algorithm simulates, and how the algorithm works step by step. After that, we will analyze the time complexity of our algorithm, talk over the pros and cons, and whether the algorithm has any use case or variance or not.
So what is bucket sort? Bucket sort, or can be called bin sort, is a sorting algorithm that works by distributing the elements of an array into a number of buckets. Bucket sort assumes that the input is generated by a random process and drawn from a uniform distribution. In brief, the elements are distributed uniformly and independently over the interval 0 to 1. Consider that the input is an n-element array and each element in the array satisfies the range 0 to 1. Bucket sort divides the interval into n equal sized subintervals or buckets, then distributes the n inputs into these buckets. After that, the elements of each bucket are sorted using a sorting algorithm. Insertion or quicksort are generally used to sort the buckets. Finally, the buckets are concatenated together in order and we find our desired sorted array. Now let's visualize the algorithm.
Let's take an array that has uniformly distributed elements in the range from 0 to 1. Here our array is A and the elements are 0.47, 0.14, 0.29, 0.80, 0.18, 0.12 and 0.49. As the array has 7 elements, the length of the array is also 7. Also, the buckets that we have taken are a 2D array or a list of lists. For each element I in the array, we determine that the index of the buckets according to the MSD or the most significant digit of the floating point number. For the first element, the MSD is 4. So we put the value in the fifth bucket, that is in the index 4. After inserting the first value in the bucket, the value of I increases. Now the current I is pointing to the second element of the array. In this case, our MSD is 1. So we put the element in the second bucket that has the index 1. Similarly, the value of I will increase for each element until the whole array is traversed. For 0.29, the MSD is 2, so it will go to the index 2 bucket. For 0.80, the MSD is 8, so it will go to the index 8 bucket. For 0.18, the MSD is 1, so it will go to the index 1 bucket. For 0.12, the MSD is 1, so it will go to the index 1 bucket. And last element, for 0.49, the MSD is 4, so it will go to the index 4 bucket. After traversing the whole array, we can see that index 1 bucket has 3 elements, index 2 bucket has 1 element, index 4 bucket has 2 elements and index 8 has 1 element. Now we will proceed to our sorting process. For easy to visualization, let's assume these boxes as buckets. And here are the array elements. After distributing the elements according to their indexes, the final buckets look like this. Now we will sort the elements in each bucket in ascending order. In our index 1 bucket, as 0.12 is the lowest among the 3 elements, it will remain as it is. Next, we will compare the second and third elements. As the third element is less than the second element and greater than the first element, the second and third elements will swap their places. As the index 2 bucket has only one element, there will be no sorting. Again, in index 4 bucket, there are 2 elements, and the second element is less than the first element, so they will swap their places. Lastly, there is only one element left in index 8 bucket, so there will be no sorting. After concatenating all the buckets according to the indexes, the final sorted array looks like this.
This is the pseudocode for bucket sort algorithm. Let's take a look at how the complete code of this algorithm works. So here is the complete code of bucket sort. The first function here is for insertion sort, and this is our main function for bucket sort. We have taken an array that has the same values as the simulation. Now the first thing we have to do is to make a list for creating the buckets. Here we have initialized an empty list as new array. Now the question is, what is the slot number here? Well, the slot number here is assigned as 10, which represents the index of our buckets. In any case, whatever our elements are, their MSD will always be between 0 to 9. Here, the MSD or most significant digit is always right after the decimal point. So our slot number will always be 10 to store all the values. The for loop here makes an empty list of lists in the range of 10. For the visualization, if we print the new array here, we can see that the major list containing 10 lists inside it. Here these nested lists are the buckets of our algorithm. The next thing we have to do is to identify the index of each element and insert them according to their location. For this, here for j in x, where x is the given array, we multiply each j with the slot number and take its integer value only. Multiplying each j or an element with slot number 10 and taking its integer gives us the index of each element. If we print the index, we can see here are the indexes for all the elements. Now we have found the index 4 for 0.4, 1 for 0.14, 2 for 0.29 and more indexes for the other elements. In new array of index.appendj, we are inserting all the elements according to their index bucket. Here, if we print the new array, we can see the elements are inserted according to their indexes. Now comes the sorting part. In this loop, for each bucket I in the new array, we call the insertion function and get the sorted elements in the bucket. Finally, we need to concatenate the sorted buckets. Here, k is initialized to 0 as an index for traversing the given array and assigning the bucket values to the array. For each element in the buckets, we are assigning the elements in the given array here. At last, if we return the given array, we will get our sorted array. If we run the IDE, we can see here is our sorted array. So this is how the pseudocode or the complete code of this algorithm works.
The average time complexity of bucket sort is big O or theta of n plus k, where n is the number of elements and k is the number of buckets. When each bucket will have only one element, there will be no sorting in the insertion sort. Besides, all the assignments and conditions will take a constant time for each. In this case, our time complexity will be big O or theta of n plus k in the average case scenario. The space complexity for bucket sort is also big O of n plus k. The worst case time complexity of bucket sort algorithm is big O of n square. When the insertion sort will work within buckets, it will take n square time to sort the elements. So the final time complexity of the algorithm will be big O of n square in the worst case scenario.
The assumption we found from this algorithm is that the input in this algorithm has to be uniformly distributed across the range 0 to 1. It is because an ideal bucket sort algorithm without any modification always works for the range 0 to 1. In the summary, we can say that the basic idea is to divide the range into a fixed number of buckets, then input each element into its appropriate bucket. Then we sort the elements within each bucket, and lastly, we concatenate all the bucket elements to have the sorted array.
Every algorithm has some pros and cons. For bucket sort algorithm, there are also some pros and cons. Let's first talk about the pros of the bucket sort algorithm. This algorithm is asymptotically faster than other sorting algorithms when the distribution is uniform. Besides, bubble sort takes n squared time in the average case, whereas bucket sort takes n plus k time in the average case. So it takes less time than bubble sort in the average case. Again, the algorithm is simple to code because it uses another sorting algorithm like insertion sort or quicksort to sort the elements. This algorithm is also good for rough sort as it divides the received array into large subsections or batches. In cons, the complications of bucket sort is that it does not sort in place. So it takes extra space in the memory to sort the elements of the array. Also, bucket sort cannot sort an array that has elements out of the range from 0 to 1. So we cannot sort integer values using an ideal bucket sort algorithm.
Another variant of bucket sort algorithm is known as histogram sort or counting sort. Histogram sort is a variant of bucket sort as it also works with one bucket per possible key value. Also, it is an efficient 3-pass refinement of a bucket sort algorithm. On the other hand, bucket sort and radix sort are called close cousins. They are called close cousins because the radix sort is also a variant of bucket sort. But the difference between them is that bucket sort goes from MSD to LSD, where MSD means most significant digit on the left and LSD means least significant digit on the right. So the bucket sort only goes from left to right, while radix sort can go in both directions. We can also use radix sort in order to sort strings, but bucket sort cannot be used to sort strings. So this is all about bucket sort. If you have any queries regarding bucket sort, feel free to ask. Thank you very much for watching.